Hi everyone, Mrs. Hanson. Just picking up with our lessons on chapter 14. We've been doing an incredible amount of work on our first functional group, the alcohols, in our chapter. And we have other groups to include, finally, some ethers, alkyl halides, and those thiols. And that's where this lesson picks up, with structures and properties of ethers. Now remember, this involves a carbon to oxygen single bond, just as the alcohols did, but ethers have two alkyl groups bonded to the oxygen atom. Those two alkyl groups can be the same or they can be different. So I noticed that this ROR, kind of that general feature, that these R groups just represent hydrocarbon chains. ROR, when I see them as this, kind of indicates to me that they're on the same alkyl chain. For example, two groups of carbon would indicate that I have an ether linkage, and that on the same side, on the opposite sides, we have the same substituent group. This we would call diethyl ether, as we learn about naming them. But if I see ROR prime, that's an indication that you're going to have different alkyl groups coming off. For instance, here I would have a methyl with one carbon. Here the alkyl branch would be called an ethyl. And when we name them with these simple names, we just alphabetize. This would be called ethyl, methyl, ether. A common name for these simplistic compounds. Now, we're going to learn IUPAC names as well, but these are just simple enough to just use common names by just recognizing what type of alkyl branch is contained on either side of the oxygen linkage. So ethers. Ethers have a bent molecular geometry, just as the water molecule does. Water, of course, has two lone pairs, two bonds to different atoms, and so does an ether. The oxygen of an ether still has two lone pairs, and it leads out to two carbon chains, just as dimethyl ether shows here, indicating about 104.5 degrees, knowing that these electron pairs kind of take up more space than the ideal 109.5 tetrahedral shape. So approximately 109.5, but the reality is they're going to be just mushed in a little bit closer due to this rich electron density on the top of the oxygen. And we see those lone pairs create a very rich electronegativity in that region, creating a negative polar region. Sometimes these ethers can be found in cyclic rings as well. A ring that contains a heteroatom is called a heterocycle, and a very specific type of ring that is a three-membered ring is called an epoxide. A three-carbon ether heterocycle, that's a little misleading. Just say it's a three-membered ring because there aren't three carbons. There's one, two, and then the third is a heteroatom. And in this case, this heteroatom is called oxygen. And this would be known as an epoxide, a three-membered ring where one of those is an oxygen. And just think about that oxygen leading down to each different R group, but those R's are connected to one another and making it a cyclic structure. So an epoxide is an ether contained in a ring, and that ring is a three-membered ring, two carbons and one oxygen. And as I mentioned, this very rich region of electron density on the oxygen, the bent molecular structure, the very nonpolar electron deficient area for the methyl groups, partial positive sign down there, and we can see that this polar bond is making the oxygen very rich, very negative charge up in this region, so the molecule indeed is polar. What is different from an ether, from an alcohol, is that there is no OH bond in an ether. Right? Because the oxygens are both connected to carbons, and therefore we do not see intermolecular hydrogen bonding in an ether, but we did see hydrogen bonding, the strongest intermolecular attraction of all that did exist in alcohols. So that means these ethers, which have, so just kind of comparison, an ether versus an alcohol, and versus just a straight chain, kind of like those boring alkenes. All molecules have dispersion forces. So ethers have dispersion, alcohol have dispersion, and even those boring hydrocarbon chains called alkanes have dispersion forces. Those temporarily in a moment in time, just a quick polarity just based on induction, and then it disappears. They also are, ether and alcohol, both are polar. So both of these will have dipole-dipole based on polarity, but not those alkanes. Those alkanes are all non-polar. Remember, those are just long, boring chains of hydrocarbon. So since they're non-polar molecules, they do not exhibit dipole-dipole interactions. And then finally, one more for the alcohol, and those were the hydrogen bonds. Because the alcohol has an O directly attached to an H, it exhibits hydrogen bonding. So you can see, just based on the studies so far, alkanes, most boring, the weakest intermolecular attractions there are. Then we have dispersion and dipole-dipole for an ether based on it being polar. And then the strongest intermolecular attractions are coming from the alcohol groups. And just based on looking at that structure, ethers have stronger forces than alkanes, but weaker forces than alcohols. They lie right between the two. So therefore, of comparable size, ethers have higher melting and boiling points than hydrocarbons, but they'd be lower than that of an alcohol. Their qualities lie right between the most boring alkane and the highly energized alcohol functional group. So here we have a straight chain. This is just a straight chain alkane known as butane, C4H10. This would be an ether. Notice on one side of that oxygen we have a methyl alkyl group, 1 carbon, and on this side of the oxygen we have a 2 carbon alkyl group. We alphabetize, so we're calling it ethyl methyl ether. And then finally over here we have a 3 carbon chain, and now we have an alcohol group. So the alcohol, the most exciting functional group, will indeed have the highest boiling point. The boiling point for the ether, significantly lower, isn't it, because of the lack of hydrogen bonding? And yet the lowest of all, the most boring molecule, the weakest intermolecular attractions would be the butane, the straight chain hydrocarbon. So let's think a minute and let's put in order the increasing boiling point. So we're looking from lowest to highest. What do you think? Look at those structures and decide what would be the lowest, then the next, and then followed the highest boiling point. Well, I see that letter A is an ether. I have cyclopentane on one side and a methyl group on the other side. Here I just know that this is a boring alkane, no functional group on there at all. And in letter C, I notice that this is an alcohol. So with A, this has dispersion forces. So does the ether. And so does alcohol, because always every molecule exhibits dispersion. And yet it's the only intermolecular attraction available for alkanes. So that's done. This is a polar molecule, so we'll have dipole-dipole interactions, and so will the alcohol. Any molecule that's polar exhibits opposite attractions, but this also meets the criteria of having hydrogen bonding. Oops, that came out messy. Let me clean that up. Hydrogen bonding, and therefore this would have the highest boiling point. This would have the lowest boiling point, and letter A would be right in the middle. So the lowest followed by the ether, followed by the alcohol. We've ranked these from the lowest to highest in that direction. Excellent work. Which of these in the pairs has the highest boiling point? Well, I notice in letter A, this is just a boring alkane, all carbons and hydrogens. And yet over here, I have an ether linkage, the oxygen. That means the oxygen is a polar molecule that has a region of negatives and positives, and therefore the polarity of that molecule will increase intermolecular attractions and therefore have a higher boiling point than the boring old alkanes. And I think letter B, you see the same thing. Letter B, I have an ether linkage, so I see a polarity to this molecule. And this is just a boring alkane. It's a cycloalkane, but it's still not very, interesting because there's no functional groups. The ether will have a higher boiling point. Letter C, I have an alcohol functional group, and I'm comparing that to an ether linkage in the second molecule. Of course, alcohols will have the highest boiling point simply because they have the greatest intermolecular attractions with hydrogen bonding available. And now I see that letter D gives me an ether, and I'm comparing it to yet another ether. So the functional group is the same. So think about what makes a molecule have a higher boiling point compared to the other is a greater surface area. And the longer carbon chain is going to have a greater surface area. It's a heavier molecule. So I mean like molar mass wise it's heavier. And so all of these increase the dispersion force. Right? The longer the molecules are, the more surface area they can kind of arrange and induce those temporary poles. The heavier the molecule, the more energy it's going to take to cause that to kind of rumble apart from one another, just due to the massive size of the first compared to the tiny ether of the second. The greater molar mass, the larger surface area creates stronger intermolecular attractions. Therefore, it's going to take more energy to force the first molecule to separate out and form a gas. And that's what boiling points do. They turn from liquids to gas. These physical properties of ethers tell us that they are soluble in organic solvents. So that's likes dissolve likes, that old rule of predicting solubility. So in other words, the organic solvents, which are always non-polar, will help dissolve the ethers always because they have non-polar hydrocarbon chains. Also, we can get them to be water soluble if they're small, very small, low molar mass. So you're looking at 5 carbons or less to be soluble in water. And that's because this polar region on the ether can communicate to the polar molecule of water if indeed it's small enough. We want these non-polar regions to not interfere, so they have to be quite small. So higher molar mass, 6 carbons or more, will not dissolve in water because as we think about having that hydrocarbon chain leading up to an oxygen and just seeing all those carbons, the non-polar region dominates that surface and prevents it from being water soluble. So label these as either water soluble or water insoluble. Well, the magic number was 5 carbons or less. This is a methyl. Over here is an ethyl. That's less than 5 carbons, so that's small enough to be water soluble. Again, we just said 5 carbons or less. Clearly a carbon on both sides is a 6 cyclic ring on both sides. So that's water insoluble. Too many carbons. Same thing here. Again, that's way more than a total of 6 carbons. So that's water insoluble. Only very tiny ethers can be water soluble. When we name ethers, this practice of nomenclature, we can assign common names if both alkyl groups are relatively small. And to do so, we just arrange those alkyl groups alphabetically and end it with the term ether. An ether linkage between a methyl, which is a 1-carbon alkyl group, and an ethyl, which is a 2-carbon alkyl group, is simply alphabetized by sharing the length of the chain as substituent names: ethyl, methyl, ether. And if they're the same substituent branch, the same kind of number of carbons, you'll hear it just in terms of di. This is called diethyl ether. No worry about alphabetizing because the alkyl groups are the same. So if we have relatively small ethers, we can just simply name the alkyl branch on either side and call it good. Let's draw ethyl propyl ether. So here is a 2-carbon chain. Propyl represents a 3-carbon chain, and they're going to have an ether linkage, which is an oxygen. So the oxygen in the center on one side leads out to a 2-carbon chain. On the other side leads out to a 3-carbon chain. Here's the oxygen, leads out to a 2-carbon chain, leads out to a 3-carbon chain. There's the ethyl, here's the propyl. And the oxygen is a bent molecular geometry. Perfect. If we have more complex ethers, we name them using the systematic name known as IUPAC, the International Union of Pure and Applied Chemistry. One alkyl group is named as a hydrocarbon chain, and the other is named as a substituent bonded to that chain. So here's an example of the substituent. If I have the oxygen linkage in 1 carbon, it would be known as methoxy. That would be naming it as a substituent of the longer parent chain. Substituent. Here is an example of an oxygen, the ether linkage, with a 2-carbon chain. So you hear ethoxy. I'm hearing that as an alkyl branch of the longer parent chain. So we say that prefix and then oxy, propoxy, butoxy, pentoxy, and so forth. So for example, this is an ether, and I clearly see this is not going to be easy to name just by looking left and right of the oxygen. So it's going to require an IUPAC name instead of a common name. Now let's find the longest carbon chain. Seems like I can find 8 carbons. Let me number the opposite direction and just double check my numbering system. I get 8 carbons, but when I number left to right, this group, the substituent group there, is on carbon 4. And if I numbered left to right, it's on carbon 5. So we want to make sure we get the lowest number possible, which makes it going to be right to left. So at carbon 4, we have this branch. Alrighty. Now I'm naming it as a substituent off of the longest carbon chain. The carbon chain that contains the oxygen is eth. And remember to tell you that it's an oxygen linkage. You hear oxy. 4-ethoxy octane. Find the longest carbon chain and name that alkane. Name the shorter chain as the alkoxy group. And so we had mentioned that there were 8 carbons numbering right to left. And I noticed that I could get the ethoxy group on carbon number 4. So 4-ethoxy octane. I'm letting you know that on carbon 4, we had the ethoxy off of an 8-carbon chain. Easy enough, isn't it? Shall we try some? Now here, letter A, we could name this really with a common name, or we can name it with an IUPAC name. Let's try both. On this particular side is a 1-carbon methyl, and on this particular side, I count 4 carbons, so I can see that as a butyl. So a common name is easy enough to come up with here, so I'll include it. And alphabetizing, we would have butyl, methyl, ether. But we can also include its IUPAC name. And the IUPAC is a systematic way of naming from the longest carbon chain. So let's find the longest carbon chain, which is here, 1, 2, 3, 4, and that becomes our root word, doesn't it? That's the parent name, butane. And now I'm going to let you know that coming off of carbon 1 in that butane, that 4-carbon chain, we have a methoxy substituent branch. Carbon 1 has a methoxy linkage. So you hear that as methoxy. I'm going to let you know that it's off of carbon 1 because it could have been coming off of carbon 2 as well. There is such a thing as 2-methoxybutane. So 1-methoxybutane is its IUPAC name, a nice common name as butyl methyl ether, alphabetized. And that was A. Let's examine B. Here I have a meth, and I could say that's methoxy, and the parent here is a 6-carbon ring. Alrighty, so that's more complex than being able to name little straight chains. So no common name I'm going to give for this one. I'm going to go straight to IUPAC. Now we have the longest carbon chain as the parent name, and that's cyclohexane. Right? Cyclohexane. And I don't need to tell you because you automatically know that at carbon 1 is a branch. I don't need to tell you that because it's top priority. So I'm simply going to say methoxycyclohexane. So you can envision a 6-membered ring with a methoxy group coming off of any carbon in the ring, and that carbon will automatically be number 1. Here we have an ether linkage, and this does look simple enough. 1, 2, 3, 1, 2, 3. Yeah, those are identical. So this is simple enough to have a common name. And since they're the same alkyl branch, we'd call that dipropyl ether. It could have an IUPAC name as well. The IUPAC name would contain the longest carbon chain, and then this as the alkyl branch. So propane is the longest carbon, and coming off of the first carbon, we have a propoxy, 1-propoxy propane, and that would be its IUPAC name, propane oxy. Is kind of what we're working through. So methoxy, propoxy, butoxy, all of those things are naming it as a substituent branch. Cool. How about some more practice? It says give it a IUPAC or a common name for each of the ethers. So here's my oxygen linkage. I have a 2-carbon chain here, so that's ethyl. And I have a 1, 2, 3, 4-carbon chain there, so that's butyl. So a common name would be simply alphabetizing. We would have butyl, ethyl, ether, all separate words. Or I could let you know that at the parent chain, the longest chain between those is butane. Coming off of the first carbon, we'd have an ethoxy functional group in a 4-carbon chain. 1-ethoxybutane. That's its IUPAC name. Letter B does not look simple enough for a common name, so I'm going to name it as an IUPAC. Let's find the longest carbon chain, which looks like 5. There's a 2-carbon chain with the oxy. So at carbon 2, we have a 2-carbon ethoxy functional group on a 5-carbon parent chain, 2-ethoxypentane. Here, the longest carbon chain is a 5-membered ring. I don't have to tell you that at carbon 1 there's a linkage because you know it's priority. So I'm going to simply say ethoxy. That's the substituent group, isn't it? A 2-carbon with an oxygen ether linkage, ethoxy cyclopentane. You did it. Sometimes going the opposite way adds value as well. Let's draw what we see for names. Dibutyl ether. So here's my oxygen. Di means I have the same branches coming off of each side. And so there's 4 carbons to each side of the oxygen. Just think about that. Here's the oxygen coming down as carbon 1, 2, 3, 4. Here's carbon 1, 2, 3, 4. There is the line structure for dibutyl ether. Letter B, we have an ether linkage. On one side is an ethyl, and on the other side is a propyl. So that's my linkage there, ethyl propyl ether. So oxygen coming down to carbon 1, 2, there's an ethyl, and 1, 2, 3 is a propyl. There's the line structure for ethyl propyl ether. Letter C. I see this root word pentane. So I see that I have a 5-carbon chain, 1, 2, 3, 4, 5, and coming off of carbon 1 is a methoxy functional group. So thinking about what that might look like, and then turning that into a line structure. 1, 2, 3, 4, 5-carbon chain. Coming off of carbon 1 is an oxygen linkage coming out to a methyl group. There's its line structure. And letter D, 3-ethoxyhexane. All right, so just kind of getting my connectivity with my first sketch. There's 6 carbons in a row. 1, 2, 3, 4, 5, 6. At carbon 3 leads out to an oxygen, and then ethoxy. Now, I just ran into letter C and D kind of, let's be sure you see that these are separated. So 1, 2, 3, 4, 5, 6 carbons in a line structure. Off of carbon 3, you see that that's leading to an oxygen, which is then coming out with 2 more carbons, 1, 2. At carbon 3, there's the ether linkage, ethoxy. Cool. We're doing great. I'm going to ask you to pause your video at this point and go into your book and do some assigned readings about ethers. Ethers as anesthetics. Diethyl ether first demonstrated as an anesthetic about the mid-1800s. I'm going to just ask that you find some interesting things to write about in your notepad. Come on back to this video when done. And we're going to pick up now with 14.9, turning our attention to alkyl halides, a next functional group that involves the halogens. The alkyl halides contain a halogen, that's group 7A. That's fluorine, chlorine, bromine, and iodine, the group 7A. And just as we did with alcohols, we can classify alkyl halides based on the number of carbons that the carbon attached to the halogen is bonded to. Here's the carbon that's attached to the halogen. It's attached to just one other carbon. We call that a primary alkyl halide. The primary alkyl halide, the carbon bonded to the halogen is just bonded to one other carbon. If we had a secondary alkyl halide, the carbon that's bonded to the halogen is bonded to 2 other carbons, a secondary alkyl halide. And of course, you see the carbon that's attached to the halogen if you go out to all other bonds and they all lead to carbons, you recognize that as a tertiary alkyl halide. How many carbons is the carbon attached to the halogen attached to? That gives us really just the same nomenclature as we discovered for alcohols. A primary alcohol, we recognized, has 2 hydrogens and just 1 other carbon, primary. If the carbon alcohol has just 1 hydrogen and leads to 2 other carbons, we call that secondary. And if the carbon attached to the alcohol has no hydrogens attached, they all let out to carbons, we call that tertiary. It's the exact same counting system for an alkyl halide as well. And so here's just kind of a visual of all that good work you put into your notes. An alkyl halide represented by a general letter X, where X represents any of the halogens from group 7A, fluorine, chlorine, bromine, and iodine. If the carbon attached to the halogen is attached to 1 other carbon, it's primary. If the carbon attached to the halogen is attached to 2 other carbons, secondary. And if the carbon attached to the halogen is attached to all carbons in opposite directions, that was a tertiary alkyl halide. So the carbon attaches to 2 other carbons leading from that halogen. That's a secondary alkyl halide. Here's an example where the carbon attached to the fluorine is attached to just 1 other carbon. So that's a primary. And of course, this carbon is attached in all directions to carbon, so that is a tertiary alkyl halide. In our examples, this is at the terminal end, our bromine. So think about that carbon is attached to 2 hydrogens leading to the bromine, and then that long carbon chain. That is a primary alkyl halide for letter A. Letter B, here's the carbon that's attached to the fluorine. It's attached to 1, 2, 3 other carbons. So that is a tertiary alkyl halide. And here's the carbon attached to the chlorine right here. It's attached to 1, 2 other carbons. Remember, this hydrogen is also attached, so that is by definition a secondary alkyl halide. We saw 1 of each in that example set. Alkyl halides contain a polar bond, so they do have a net dipole. They do not meet the criteria for hydrogen bonding, however, and as a result, they have higher melting points than straight-chain boring old alkanes, but lower boiling points than the very exciting alcohols. So they're very similar in properties to the ethers. We would put them between the boring alkanes, but less exciting than an alcohol group, which has hydrogen bonding criteria. So a very polar bond between the carbon leading out to the halogen. This is a very electron-rich area, making the carbon electron deficient. And so that region of polarity is set up. The net dipole is around this chlorine with a very rich negative area. And so that affects the boiling points. Here we have a chloroethane, chloropropane, this one I guess is bromopropane. What do we notice? That the boiling point begins to increase as the size of the halogen increases. So here we have like a molar mass consistency. The molar mass of CH3CH2Cl is the smallest. And if I take off a chlorine and I add a big old bromine, which is much heavier on the periodic table, this has the largest molar mass. So it's the heaviest, it would have the highest boiling point. So let's put low molar mass, smallest or lowest boiling point. Whereas here we have a very high molar mass. Just think about it maybe by saying the largest, bromine is larger than chlorine. Remember the fluorine, chlorine, bromine, iodine. This is group 7A. Fluorine, here's a little bit bigger chlorine, here's a little bit bigger bromine, and here's the massive old iodine. Atoms get bigger as you go down. Atoms get heavier as you go down. Therefore, the halogens, the heavier they are, need more energy to force them to boil. So as the size of the halogen increases, the boiling point also increases. Longer carbon chain, higher boiling point. Bigger the halogen, higher boiling point. So let's compare these compounds. It's just practicing that idea. I have a carbon chain. It looks to be the same in all of these. Yep, they're all 3 carbons long, right? So really the only difference is the halogen that's placed on the terminal end. A fluorine, a chlorine, and iodine. So the smallest halogen, which I mean also in terms of size, but it's the lightest molar mass as well, is going to have the lowest boiling point. Whereas iodine is the heaviest in terms of molar mass, and it's the largest surface area. It's a big old atom, meaning this is going to have a very high boiling point. And chlorine would lie in the middle. So the first CH3, CH2, CH2F. In the middle, we would place CH3, CH2, CH2Cl, and the heaviest would have the highest boiling point, and that's our ranking there for letter A. How about B? Well, this is interesting. This right here is kind of a boring straight chain alkane. I don't see any halogens at all. Okay, so boring. Very few intermolecular attractions. So now, here's bromine and chlorine in a straight chain. So I can see the weakest intermolecular attractions are going to come from the most boring molecule, CH3, CH2 taken 4 times, CH3. That's an alkane, A-L-K-A-N-E, alkane. Very low boiling points. They're boring, no functional group to create any type of intermolecular attractions. Then I would rank the chlorine next. We have a CH3, CH2 taken 5 times, Cl. And then the heavier halogen, CH3, CH2 taken 5 times Br. This heavier halogen creates a stronger intermolecular attraction, so therefore a highest boiling point. And that's our ranking there for letter B. To name alkyl halides, we give the IUPAC name of the following as an example. And very similar rules to what we've been practicing. Start by finding the longest carbon chain that contains the alkyl halide. Alrighty, so here I have a 1, 2, 3, 4, 5, 6, 7 carbon chain, making that parent chain called heptane. So step 1 of naming this structure, we found heptane to be the longest carbon chain. At carbon 2, I see a chlorine. You're going to hear it called chloro as a substituent branch. And here is a branch with a 1 carbon, so we hear it called methyl. Alrighty, so I can see there's some branching coming off of a 7 carbon chain. Make sure the halogen has the lowest possible number it receives the priority over the other substituent carbons. Number the chain, giving the halogen the lowest number, and then therefore this becomes 2-chloro. Then I see a 5-methyl and the parent chain heptane. Carbon 5 had a methyl. Carbon 2, chloro. And putting that together, we come up with 2-chloro, 5-methyl heptane. When I wrote that, I was just checking I did that correctly. 2-chloro, 5-methyl pentane, alphabetized. Perfect. Should we try some? 1, 2, 3, 4, 5, 6 carbons in the longest chain, making sure that you see carbon 2 is the lowest possible number for that bromo. The alkyl group with the halogen on it is bromo. And here we would have just 2-bromohexane as our name for that alkyl halide. 1, 2, 3, 4, 5 carbons in the longest chain. 1, 2, 3, 4, 5 carbons in the longest carbon chain. So I numbered on purpose, right to left, left to right, so we have a decision to make. Notice that either direction gives me 3 for the chlorine. So I need the methyl group to have the lowest branch as well. So there's a methyl, here's a chloro. Remember to alphabetize. 3-chloro, 2-methyl, and that's a 5-membered branch, so pentane, alphabetized. The priority goes to the halogen in that 6-membered ring. So I'm going to tell you that at carbon 2 we have a methyl, and at carbon 1 there is a bromo. So when I'm naming that, I automatically know that at carbon 1 we have a bromo, right? And so 2-methyl bromocyclohexane. Do I like that? 2-methyl bromocyclohexane. Now, this is all one word. Because it does not get a number, I'm not alphabetizing bromo and methyl, right? This is the parent name. And so the parent name involves the halogen already. So I'm not alphabetizing substituent branches. The bromo is part of the name. And therefore, the only substituent I have to number is the methyl. 2-methyl bromocyclohexane, because I know that that's number 1. So I don't say it in the name. I would not write 1-bromo, 2-methyl cyclohexane. And the reason is this is not needed because the halogen gets the priority. I know it's on carbon 1 and it becomes part of the actual parent chain. All right, good, good, good. We're seeing all kinds of good examples. Let's try the opposite direction. 3-chloro, 2-methylhexane. All right, so that's a 6 carbon. So I just like to get that parent out, and I'll just number them. 1, 2, 3, 4, 5, 6. At carbon 3 is a chlorine, and at carbon 2 is a methyl. All right, so that's kind of the connectivity. 1, 2, 3, 4, 5, 6 carbons. There is a methyl group at carbon 2 and a chlorine at carbon 3. Easy enough. Ooh, let's see what's going on with B. We have an octane dimethyl. All right, so I'm going to draw 8 carbons. There's 8 carbons. Let me just number those. Let's see, at carbon 4, we have an ethyl group. At carbon 5 is an iodo group. At carbon 2, we have methyls. If we had numbered the opposite direction, we would have had 4 iodo, we would have had 5 ethyl, and we would have had 7,7 dimethyl. This obviously is the lowest numbering system, so that's why we want to make sure all substituent branches get the lowest number possible. So that's why I'm not going to go this direction, because 7,7 versus 2,2 is the winner. 2,2 is a lower system than 7,7. So we're working for all branches to get the lowest number possible. So I have, let's put this together. We have 1, 2, 3, 4, 5, 6, 7, 8 carbons in the longest chain. Carbon 2 has 2 methyl groups. Carbon 5, 1, 2, 3, 4, 5 had the iodine, and carbon 4 had an ethyl group. So there's the beginning of that line structure. Excellent. Let me give myself some room for letter C. And this one is telling us 1,1,3-tribromocyclohexane. There's this cyclic structure. 3 bromines, 2 of them coming off of carbon 1, 2, 3. Notice that the numbers are required for all branches. When there's more than one halogen, I have to tell you where they're located. So if you had just heard me say bromocyclohexane, you knew there was 1 bromine on it. Could have been any of the 6 carbons. But since there's more than 1 bromine, I have to tell you the location of all of them. So that's why you see 1, 1, 3, all 3 numbers required to tell you the positions of those 3 halogens. And letter D is a common name, propyl chloride. That's just telling me there's a chlorine at the end of a propyl branch. You would call this an IUPAC 1-chloropropane. So there we turned a common name into an IUPAC name. So here you would just have 1, 2, 3 carbons with a chlorine coming off the end. Perfect. Oh, we're doing good work. You're also going to jump into your book now and do some interesting alkyl halides reading. So go in and pull out some informative, interesting topics that you'd like to write about some interesting alkyl halides. And we have one more to come back to, and that's your sulfur-containing organic compounds. So that last section of reading, and then we're going to finish up the video here with our sulfur group. The thiols. Remember, thiols contain a sulfur, a sulfhydryl group, SH. Remember group 6A on our periodic table had oxygen, and right underneath that is sulfur. You're going to see a lot of similarities between a thiol and an alcohol. It also has a bent shape because it also has 2 atoms and 2 lone pairs from its bonds. Sulfur being just below oxygen on the periodic table have a lot of similar physical and chemical properties that relate to alcohols, including its molecular geometry being that of oxygen's alcohol functional group as well. They're both bent, just like a water molecule is bent. So the bond angle would be approximately 104.5, which is just a little bit less than the ideal 109.5 bond angle for a tetrahedral electron shape. So these thiols contain no OH bond, so there's no intermolecular hydrogen bonding, right? Because it's an SH bond, so there's no H bonding. Puts them right into that similarity between ethers and alkyl halides because they're polar, but there's no hydrogen bonding. So here we have an OH that has the strongest type of intermolecular attraction possible with a boiling point of 78. If I substitute out an oxygen for a sulfur, we have a lower boiling point at about 35. So OH, strong attractions, high melting points. The thiol, still a dipole moment, still a polar molecule, but not the significance of hydrogen bonding, so you'll see the boiling point lower. And to name that thiol in the IUPAC system, you name the parent hydrocarbon just as an alkane, and we add the suffix thiol. So number the chain to give the SH that lowest number possible, and we simply add the ending thiol to let you know there's an SH group. Notice we're not dropping the letter E. We're saying the alkane parent name as is, and we just add on the ending thiol. Methane thiol, all one word. 1-propane thiol, all one word. This would be called 2-propane thiol. And that tells me the SH functional group is on carbon 2 of a 3-carbon chain. We can practice. Here's an example where we're learning how to name a thiol, given a kind of a step-by-step fashion. I recognize the thiol functional group, so I know that the ending will have a thiol last suffix. Here I'm noticing that I have an ethyl alkyl branch as well. Let's find the lowest numbering system possible for these branches. Looks like I have an 8-carbon chain. At carbon number 2 is a thiol, and at carbon number 6 is an ethyl. So we number that chain, number to put the SH at carbon 2, and we're going to number to put the ethyl at carbon 6. Alphabetize here, so we had at 6 ethyl, we have a thiol group at carbon 2, but we don't say it in before the name, we say it after the name. So that's 6 ethyl, 2 octane thiol. Don't drop the E, just add the ending thiol, and now I know it's at carbon number 2. Let's keep practicing. 1, 2, 3, 4, 5 carbons. At carbon number 3 of a 5-carbon chain, there is a thiol substituent group. Excellent. Here we have a cyclic structure, a 6-membered ring. I don't need to tell you at carbon 1 because you'll know the priority is given to the first carbon when we see a substituent group. I will call this cyclohexane. Keep the E and then add the ending thiol to let you know there's an SH group off of the carbon. Now let's see, here's carbon 1, 2, 3, 4, 5, 6, 7, 6, 7. So I get either way. At carbon 1 is a thiol group, and at carbon 5 is an ethyl. What did we say? 7? So that's heptane thiol. At carbon 1 is an SH. At carbon 5, there's a 2-membered carbon chain, ethyl. 5-ethyl, 1-heptane thiol. Thiols have characteristic stinky smells. They smell foul. Sulfur smells like a stink bomb. And they can be oxidized to disulfides. These disulfides contain a sulfur to sulfur bond. So this disulfide is the elemental connection between two like elements. Sulfur is UR. That's what I'm trying to write. There we go, a sulfur to sulfur bond. This bond right here has a special name called a disulfide linkage. 2 units of a thiol can be oxidized. Remember that O, oxidized. And that's going to increase the carbon to sulfur bonds. You can think of it as reducing the number of sulfur to hydrogen bonds. Oxidize, increase the carbon to sulfur, and reducing the sulfur to hydrogen bond. So I'm going to break a bond between the sulfur and hydrogen and link together the 2 sulfurs. Now I can use 2 like molecules to do that, or I can do 2 different thiols to perform the same function. When we oxidize, we convert to a disulfide. We can go right back and reduce our disulfide into the thiol as well. The disulfides can be converted back to thiols with a reducing agent. So if you see oxidizing agent or reducing agent, that's telling us break the bond between the 2 sulfurs and add the hydrogens back. Since I have 2 like thiols, I produce 2 molecules of the same compound. These organic sulfurs are actually just kind of an application, an interesting topic here. In our hair, to make straight hair curly, remember in the good old days where people would put perms in their hair, you'd get a permanent wave, and that solution would break apart the sulfide bonds so that when you put it into a curler and applied another chemical, they would reform the sulfide bonds into a curlier fashion. So they broke the disulfide here, curled it up, put another chemical on so they could reform it, and now it would hold its shape as a curly member. Let's draw the disulfide formed when 1, 2, 3. This is called 1-propane thiol is oxidized. So I have a 3-carbon chain. To oxidize says I'm going to create a disulfide bond, and we're using the same molecule to do that. That's it. That's all there was to this problem. A disulfide bond forms. So to be oxidized, you form an SS bond. Here is the thiol functional group. We're going to do 2 like molecules. I'm trying to draw that cyclic structure. Oh, Linda, let's try again. 1, 2, 3, 4, 5, 6. And it leads out to a sulfur. It's going to attach to a sulfur. And I have to draw that 6-membered ring again. Hey, that one wasn't so bad. So I'm forming the disulfide through a process called oxidation. So here I have a thiol group. There is 5 carbons in that chain. 1, 2, 3, 4, 5, leading to a sulfur, going back out to 1, 2, 3, 4, 5 carbons. So you'd have 1, 2, 3, 4, 5 carbons, S bonded to S, and then 5 more carbons. We're forming a disulfide bond through oxidation. Draw the product form when the disulfide is reduced. So notice here we've got to find the sulfide bond and then just break it. So I have 1, 2, 3, 4 carbons. And if I go back to the thiol, I would have butane. Well, I'll tell you what, carbon 1. There is a thiol, so that's the first product. And on this side, there's a 2-carbon chain. So here, putting back the thiol group to a 2-carbon chain, you would have ethane thiol. So just cut this molecule right there, broke that disulfide bond, go back to thiols, means add hydrogens back onto the sulfur. These had 2 different carbon branches on that disulfide bond, so we're going to get 2 different thiols. In this example, here is the disulfide bond. Putting the hydrogen back on will create methane thiol, and that's a 3-carbon chain. So here we would have CH2, CH2, CH3. That's 1 propane thiol. And this would be methane thiol. No number needed. Cool. Here is the disulfide bond. Not disturbed at all. I'm adding the thiol group back on. And here we have the HS restored. And now I'm just going to finish a CH2, CH2, CH3 in terms of the 2 products, returning them to thiols. Breaking the disulfide bond is a process of reduction. Forming the disulfide bond is a process known as oxidation. And we've done it. We have practiced all of those functional groups found in chapter 14. You're ready to go and start some homework, preparing for a quiz as well. I enjoyed talking with you.